Okay, hi folks, we're going to have a look at a question now that uses some variable acceleration. Woohoo, alright, okay, that's the guy's expression there when it comes to that. Now the idea is variable acceleration, you can't use your standard Suvat equations, they only work for constant acceleration. Now, we have got a bit of a clue to this though, because when we were thinking about like the velocity time graph, how do we work out the acceleration from it? Well, we found out what the gradient was of the graph. So in order to deal with these questions, this is what you see in your textbooks, that in terms of acceleration, the acceleration can be calculated by thinking about the differential of the velocity. So basically what we're saying is how the velocity changes with respect to time, that is what acceleration is. And that sort of makes sense, doesn't it, if you think about it? So the change of velocity with respect to time gives you acceleration. So essentially all we need to do, if we need to work out acceleration, we can just differentiate something in terms of v. Likewise, if we think about it, carries on the same, logically, what is velocity? You know, if you're saying that, velocity, well, that's a rate of change of distance with respect to time or displacement. So logic would say that v equals ds by dt. So, you know, I'm driving at 64 miles an hour. Miles, literally, is distance. So it's how much miles I'm covering with respect to time. And that obviously makes sense. So again, just to differentiate to go from this in order to calculate the velocity, that makes sense. Working backwards, however, what's the opposite differentiation? Integration, which tallies with what we've seen before in terms of area under a graph. Think back to that velocity time graph. If we were looking underneath the velocity time graph, it gave us the displacement. And so logic would say that if we have s, we need to find that out from velocity, we need to integrate the velocity with respect to time in order to work out our displacement. Okay, logic would say using a graph. I'll just always give an extra caveat. It's worth bearing in mind. Obviously, you can see it's going to give the area under a graph. So if you've got this, there, nice and straightforward, there's the distance or displacement under the graph. Always bear in mind, if you are literally going to integrate though, if you're integrating between there and the graph happened to be shared like that and cut underneath, what would happen? Well, calculating a calculator, by integrating that line there, these two cancel each other out and give 0. In theory. Now, logic would say displacement, yeah, that's like me saying drive, 60 miles an hour, whatever it is, away from work, slow down and come back again. Overall, you've literally not covered any distance, displacement, but you have in fact covered distance because you went away and then came back. So always bear in mind if the question is after distance or displacement, because in theory, you need to split your integral if you needed to do that separately and work out how far you travelled in total. And the other one, of course, is v is the integral of a with respect to t as well. Anyway, let's see how we get on using these questions. So the first one here, number 1, we've got a particle travelling in a straight line. Velocity is measured at t seconds after it passes through a point A as 0.6 t squared plus 3 meters per second. Find the velocity of p when it passes through A. Well, at point A, as it passes through, what do we know? Well, t is 0. So when t is 0, and we're looking to work out what the velocity is, just need to substitute that in. So v is 0.6 times 0 squared plus 3. That's nice and straightforward, 3 meters per second. I like that question. It is only worth 1 mark. The next one's a bit trickier. The displacement of p from A when t is 1.5. So we're working out a displacement, and we've got a formula, v equals 0.6 t squared plus 3. Well, the idea now is, if we've got that, we need to work out displacement, we need s. So we're going to use this. So s is equal to the integral of 0.6 t squared plus 3 with respect to t, of course. And then we read the question when t is 1.5. Well, we started off at 0 as well, so it's basically from 0 to 1.5 of our integral. So if we do that now, integrate 0.6 t squared, add 1 to the power, so 0.6 t cubed, all divided by 3, and 3 will just go to 3t, that between 1.5 and 0. So 0.6 divided by 3 gives me 0.2 t cubed plus 3t between 1.5 and 0. So if I substitute those in, I've got 0.2 lots of 1.5 cubed plus 3 lots of 1.5 total, and then I'm going to take away 0. So 0.6 is basically 0 cubed is 0 and 0, so it's because we take away 0. Nice and straightforward. So I get my calculator out here. What have I got? 1.5 cubed. It gives me that, times 0.2, and then I'm going to add 4.5 on, gives me 5.175. So 5.175, and that will be in metres because it's a displacement or distance. Okay, moving on to part 3 now. We've got the velocity of p when it has acceleration 6 metres per second. So again, let's think about it. We know what v is. V is 0.6 t squared plus 3. But we're being asked a question about acceleration. You know, we've got to work velocity out, but we need to know when the acceleration is 6. So real terms now, what are we going to do with that? Well, we need to work out what the acceleration is. So acceleration is dv by dt. So we're going to do a bit of differentiation. We'll differentiate a 0.6 t squared plus 3. And so if we do that, bring the 2 to the front, so it gives me 1.2 t, the 3 disappears. We know from the question, it's saying when it has acceleration 6 metres per second, so that's going to equal 6. And so from that, we can work out that t must be 6 divided by 1.2, which is 5, I think, 5 seconds. And so now, in order to work out the velocity of p when acceleration is 6, if I put my 5 seconds back into the original thing, so v is 0.6 lots of 5 squared plus 3, which is 0.6 times 25 plus 3, and that gives me, what's 0.6 times 25? 15 plus 3, which is 18 metres per second. Okay, and that would be the question. Okay, all right. So there's an example of some variable acceleration. Thank you.